Let's talk about variable selection for this week. Well, you might have the question in your head, the difference of variable selection and model selection, like we discussed the last week. Well, the model comparison, model selection we talked is more for selecting a parameter like the degree of polynomials or the number of neighbors you consider in K and N. So that's more for the parameter in the model. So, and for variable selection, we're still comparing models, but with different variables to be included in your model. And hopefully you will get better idea, like the difference of variable selection we will learn right now. Comparing to last week's material. Okay, let's go ahead, start with this. So some logistics about today's material. Um, you can refer to the chapter 6 of this Introduction to Statistical Learning with R and chapter 7 of this modern approach to regression with R. So I currently, oh, sorry. I don't know how to pronounce this. My lips is not working. Ironically, the approaches in this book, they are not more than enough. So we need both of this chapter 7 and chapter 6 in James' Introduction to Statistical Learning. Well, anyway, it's a combination of these two chapters to be included for today's lecture. Okay. Well, if you have the question like why we want to do this variable selection and what we are doing for like for this week and the following weeks, well, I want to kind of extend the linear framework for more material, like how we can continue to use linear model, but extend and improve the model framework by like doing this variable selection. You can alternatively, doing variable selection and also doing some alternative fitting procedures, like replacing the list of squares that we've learned previously. And we will continue to use the linear models because they have the advantage of easier inference. So that's the big part for the linear models. And well, why would we change? We would want to change the fitting procedure. That's for the purpose of better prediction accuracy and model interpretability. Okay. So prediction accuracy, you know it. We want to like comparing to we've talked about the testing data set. In testing data set, we want the prediction to be more accurate, more close to the data that you know that's the true the true result. And for model interpretability, that it's a big part for statistics, especially if you like work in industry, you have to be able to interpret your model to the audience. Okay. And model interpretability is important. And your ability to interpret the model is important as well. Okay. Okay, let's talk a little bit more about the prediction accuracy. So, well, if let me show all of this to you. So we've had the assumption that we're assuming the model or the data we have, it is a linear relationship between y and x previously, like when we do the linear models. But now we kind of make the assumption a bit looser, like, I mean, make it more flexible. We're not restricting, it has to be linear. At least, actually, even if we are assuming they're linear, they are, well, not necessarily being linear, right? But if the relationship between the response and the predictors y and x, they are approximately linear, then the least square estimate will have low bias. If you still remember the LSE, the least square estimate, they are actually unbiased if it is a linear relationship, okay? But now the restriction, the assumption is released a little bit. So if, let's consider like the sample size and the number of predictors you will include in your model. So this P is the number of predictors you will include in your linear model. If your sample size, the number of rows in your data, they are far greater than the number of variables included, then the least square estimate will also have low variance. So beside it has like low bias, it would also have low variance. So the model will perform really well if you do prediction on your testing data set. Okay, that's what it means. Like it has lower variance. Like if you change to a new data set, it would not perform really different, really bad on the new data. But if P, the number of predictors in your model, is close to your sample size N, then there will be lots of variance in the least square fit, which will cause overfitting and poor predictions on your testing data set. Okay, so we're comparing P and N. So if we're using a large P, we can see like what is the price to pay. Okay, so if P is greater than N, so even larger P, then there isn't a unique least square solution. So you won't be able to find the LSE at all. Well, no fixed LSE. And the variance would be infinite, and the method, basically you cannot use it. Okay, so you see if you use really big P, especially if they're greater than your sample size, then it would be a disaster. Well, you probably get the idea of there is a trade-off if you like increase the number of predictors in your model and or use a less like a smaller model. And the trade-off is between the bias and the variance. Okay, and constraining or shrinking the estimated coefficients, like controlling if you use larger P or smaller P, it will raise, yeah, this is constraining shrinking, like use a smaller number P, it will raise the bias, but it will reduce the variance by a significant amount. So having a smaller P, you use fewer coefficients, fewer variables in your model, it can lead to significant improvements in accuracy for predicting on your testing data set. Okay, I'm emphasizing using testing data set for like evaluating this performance of your model, because we learned if you use the training data set, as you increase the number of variables, it will get better and better on your training data set. But when we compare models, we would have to evaluate based on testing data set. Okay, just a refreshment on that important part. Using testing data sets for evaluating models. Okay, and another aspect is this model interpretability. I mentioned, well, actually, some of the variables you use in multiple regression models, they are in fact not really associated with the response. Okay, even if you collect so many variables, they may not necessarily really connected to your response y. Well, including the irrelevant variables, it will lead to really complex model, and normally it will be not unnecessary complexity in this model, and it will make the relationship harder to determine. Like for R, it's harder to work with a complex model. And by removing these variables, we can obtain a model that's more easily to be interpreted. So excluding irrelevant variables is called variable selection, or sometimes it's called feature selection. Like feature, this word probably be more often used in industry. Well, yeah, we will call it variable selection anyway in this class. We have, actually, there are many variable selection methods, and we will discuss only two of them, subset selection and, oops, oh, well, anyway, because, yeah, we will talk about subset selection, which is in this chapter or in this week. And for next week, we will talk about shrinkage. Well, the difference of these two, when we do subset selection, this is the classical way to approach this variable selection. And you find a subset of the predictors and you fit a model with least squares on those. Okay, find a subset of your of the variables. And when you do shrinkage, well, we will talk about more next week. That is, you fit a model with all your predictors, but fit it in such a way that the estimated coefficients, they are shrinked or regularized towards zero. So when they are really shrink to zero, that means they will just disappear from your model, okay? Yeah, we will talk about subset selection today. Well, subset selection, this problem would have two parts. The first one is, how do you select the subset to check which of the choices is the best? And we'll compare, we can do best subset among all the possible combinations of your model, and also stepwise selection. So this is how you do the selection. The second part is, how do you decide which is the best? What is the criteria you will use? And what is called the best? So remember, we learned R-square to compare models. And also we know that the R-square will increase monotonically with more features. If you include more and more variables in your data, in your model, the R-square will just increase. But we know it's not really good if we just dump all your variables in the model. It may not be necessary. And also this residual sum square, RSS, will also decrease as you add more features. Okay, and this plot I took from the book, from Jim's book, that is showing x-axis is the number of predictors, and y-axis is the residual sum square, and this plot is the R-square. So you notice the residual sum square will just decrease. Well, it will go to like flat if you for this particular example, but the overall it will decrease as you include more and more variables, and R-square will just increase if you include more variables in your model. Okay, this is a two-part. I think we'll talk about best subsets at this point. So this best subset selection, we will start with the most thorough option for subset selection. So we will fit a model for each of the 2 to the power of p possible combinations. So that's all possible combinations with among your p variable that you have. Okay, so how we exactly do that? So we fit the p models that have one predictor. So this is your first step. You fit p models, each have one predictor, and then p choose 2 models, have 2 predictors, and so on. And we will choose which of this is the best. Okay. And choosing the best from the 2 to the power of p possibilities is not trivial. Okay. And we can use R square or RSS to compare models of the same size, but not models of different sizes, because we said if you increase the number of variables, R squared will definitely go up, and residual sum of squares, RSS, will definitely go down. So different size models, you cannot use R squared and RSS to compare them. Okay, let's formally talk about this best subset algorithm. So if we let this M0 denote the null model, which contains no predictors, so M0 predicts the sample mean Y bar for each observations. So if you have no predictors at all in your model, the prediction for all your observations in your testing data set, like in your model, when you in training, you will have the sample mean for each observations. And for when we increase, so for k from 1 to p, we will fit p choose k models that contains k predictors. And we pick the best among these p choose k models and call it mk. Okay, we'll denote this m by this subscript k. And here the best is defined as the model with the smallest RSS or largest R squared. So now we're comparing model of the same size. So all of them would have k variables, k predictors, and we compare their RSS and pick the best from this p choose k models, and select the overall best among, select the overall best model from your p+1 individual best. So you have M0, that's this one, and this p is, this p is from this p choose k models. So each of them you will have, for each particular k, you will choose one best individual model and plus this M0. And use this p+1 individual models, you will compare, you will do cross-validation and cross-validated predictor error. So you can use this prediction error to compare this p+1 models. And you can also use this CP, also called AIC, as a metric to compare your p+1 models, or BIC, or R square adjusted. So that is adjusted R square. That one you can use it to compare model of different size. Okay, so yeah, this is the algorithm for best subset selection. Well, I mentioned it's not trivial to do this best subset selection by checking all the possibilities, because it's like very it's very computational expensive. As p increases, the number of possible models will grow rapidly. So some examples here, if p equal to 10, you would have to compare 1024 models. And if P increase to 15, this many models. And if you increase P to 50, so you can tell how many models you have to compare. So that's the disadvantage of this best subset. But anyway, when you have relatively small number of predictors, we can still use this best subset, and we will learn how to use it in R. Okay.